the last talk by Zvi Bern. Last lecture.
Okay, well, thanks a lot. So in the last lecture, we worked out the graviton amplitude, the one-loop graviton amplitude, in terms of box integral, cross-box integral, then some triangles, and we had certain coefficients here. And actually, if you look carefully, you'll notice that there's this piece here is proportional to the tree level squared. And this thing in the current form is not directly useful because it's an amplitude, and at the end, the people who do general relativity, classical mechanics, they want some object that they can use, either a Hamiltonian, a scattering angle would be good, a classical scattering angle. So what we have to do is we have to remove the iteration, because the scattering amplitude, it contains, maybe I can just draw it like this, it's just this box integral. It contains a piece that's the tree squared. And the tree squared we are uninterested in because we already know what the tree is. So we have to take it out of the amplitude. So how are we going to take it out of the amplitude? Now there are ways of actually analyzing the amplitude directly and just taking it out directly in the amplitude, but a much more straightforward way of doing it is by EFT matching. That we use an effective field theory to define what we mean by the potential. We calculate a scattering amplitude in that effective field theory with that potential, and then we match it to this thing. And by matching to this thing, we can then identify the new contributions to the potential. Yeah? And the iteration is automatically taken care of. And what our EFT looks like, so to remove iteration, use EFT matching. And this EFT is precisely an effective field theory of two black holes with a potential, scattering through a potential. So we have a potential, V of P and P prime, and that potential we can define, there's the lowest order term, we'll have a scattering process. So there's some scattering, there's a potential here, so that's the potential there. There's, we have P coming in here, minus P, we're working in the center of mass, and then P prime goes out. And there's a minus P prime over here. So this is coming in, and this is going out. And the potential is just the Newtonian potential plus its corrections, P minus P prime. P minus P prime, I should probably put a vector symbol there. This is momentum transfer, Q. And then there's a coefficient. The coefficient is what we calculate by matching to the full theory. So this was the tree level coefficient that we worked out. And then the next order, 2 pi square, and then a C2. Oh, this should be squared, P minus P prime, like so, and then plus order G cubed. Okay, and these coefficients are what we're interested in. That defines the potential. This one we already know. We don't know this one. Okay. There's maybe a little point here. We have to be a little bit careful about how to define this, because the way we're going to use this EFT is we are going to use this theory, which let me write down the kinetic term, L kinetic of that, of one of the black holes. So that would be A dagger minus K I dt minus the square root of k squared plus, let's say, black hole number A. Okay, I should sum, it's the sum over both black holes, A of k. So this is the kinetic term, and you'll recognize this. Oh, this looks exactly like the field theory that you're used to, except it doesn't have antiparticles. Why no antiparticles? Because it's a low energy effective field theory, there's no antiparticles. But this is a relativistic particle, right? And then the other part of the Lagrangian is just defined by so the interaction of that Lagrangian would be defined by, I have an A dagger of k, A of minus k, and then the other field, this is one black hole, the other field would be k prime. This should be k prime, and this would be minus k and with a dagger, and this is b of k, and then the potential v of k and k prime. Okay, and that defines a 4-point interaction. So the 4-point interaction is the potential minus I times v. Okay, and then I go ahead and I start calculating in this theory. So if I want the scattering amplitude, then what I do in this EFT is I take lowest order, that's the lowest order diagram, one potential, and then I calculate a loop like so. Okay, plus dot, dot, dot. Now, one thing that you have to be aware of, this is the potential. The potential is higher order in G is included in here. So inside here is G and G squared. So there's one potential here, there's a potential here and here, so it's two potentials. So here I only need the G term. And then you may notice right here, I'm taking it off shell, right? I'm supposed to integrate over the momentum around that loop. There's a loop momentum here, right? So there's maybe a little thing we have to be careful of. This coefficient here, how do we define it in terms of the P and the P prime? So there's some arbitrariness in doing this. I will just make a choice that I know is a good one. It leads to nice potentials. Remember, potentials are not gauge invariant, so some place there's an off-shell continuation, and then the details of exactly how I do it. If you go home and you do it some other way, you will get a different potential. That's okay. Nothing wrong with having different gauges, different coordinates, right? As long as you can match to the gauge invariant amplitude, we have to get the same answer. We have to match to this. Then you have a good potential. There are many potentials that are good, but some are better. So in fact, the one that is a good one is, so before we, if everything is on shell, see, if this is on shell, let's say that you're looking at the potential, this is on shell, this is on shell, there's energy conservation, so you get that P square equals P prime square, so there's no difference between the P and P prime except the direction, right? Because energy is conserved, center of mass, and so forth. However, if we could take it off shell and we're going to have an integral. Some technical difficulties. And we're going to have an integral over the momentum. When you integrate over that momentum that's in here, then it will no longer be true that the square of this is the same as the square of that. It's some off-shell continuation. So in fact, the way we will do it is we'll take that coefficient and we will average in the following way: P squared plus P prime squared vector. Okay. So it's this coefficient in terms of these momenta, instead of making it of p squared, before it was of p squared, the coefficient was a function of the p squared. But now, because of this off-shell continuation, we have to make some choice. So we'll do that choice. And if you don't like that choice, that's okay. You can go home, try a different choice. You'll get some different answer, different potential, but the point is the equation of motion will be the same. I don't have a theorem that that's true, but you could say logic dictates this, right? Because we know that potentials are not gauge invariant. There are many potentials that give the same scattering. So the whole name of the game is, as soon as you can find some definition, there's some potential, right, that's continued off shell in some way, that generates the correct amplitude, everything should be fine, right? The physics is on shell. The essential information be captured on shell. And if there's anything you learned in this school, that's what it is, right? In perturbation theory, all information is available on shell. So the key is that whatever I do here, we have to match to the on-shell amplitude that we calculated here. Okay, and whatever we get out should be a valid potential that we can use for classical mechanics. That's the basic logic. And the same thing for C2. We're going to make it a function in the following way. So it's some choice that experience shows is a very good choice of how to do the off-shell continuation. Okay? So we now need to calculate in this theory. In this theory, there will be an iteration contribution. Right? This is a tree here, this interaction here. By the way, this interaction, even though it looks like a point, look here. It's not a point, there's a propagator there. That's the graviton. Okay, it's potential, it's a potential mode, so there's no time propagation. It's a point as far as time is concerned, but momentum, it's non-local. Okay, so maybe this shouldn't be drawn as a point, but there's a potential sitting there, explained right here. Okay. We have to, yes, here. There's an iteration in here that should match exactly this iteration. If we can make that match work, then we know we're doing things correctly, and that takes care of the iteration, because if you get the iteration in the effective field theory, and it matches the iteration that you have from here, you just subtract it off from both sides. It's not important. What you have left over is the non-iteration term. This is the piece we're going to go after. Right? It's this contribution. Iteration comes from this thing iterating. Non-iteration, that's the piece we want. Okay. So we calculate by Feynman rules. Yes, you are allowed to do Feynman rules in this class because this is an effective field theory, so it's really easy. This is a pretty simple theory. This is definitely not general relativity. So, or you could say it's a simplified version of general relativity where we write everything in terms of the potential. Okay, so what do the Feynman rules look like? Well, there's a propagator. The gravitons don't propagate. We don't need a graviton propagator. It's already in the potential. So the line is omega minus the square root of p squared plus m squared. Okay. Then we have this little dot there, and that thing is minus I times the potential. And that potential we give over there. C1 is already known. C2 is what we're trying to determine. Okay. And then the amplitude, following the Feynman rules, we can write it down immediately at g squared from the EFT that we have just created. So this represents a scattering amplitude, two black holes, they come at each other, and there's a potential interaction between them, and then we want to calculate a scattering angle or scattering amplitude from that, just following normal Feynman rules. Okay? So minus IV plus the integral minus IV, and we should, so P and K, maybe we should draw the picture. It's that picture. I'm just, this thing will be, that's the first term, and the second term is this diagram. Okay, so IV, that's this corner here. Then in the middle I have, there's two matter propagators, so I write that down. Let's call this thing is G of omega and P. So this one, let's call this G of omega and K. This momentum here will be K. G of minus omega, so that'll be on the other side, on the other loop, minus omega plus E1 plus E2. Let's label where nothing goes. That's 1 and 2, 1 and 2, 3 and 4, 3 and 4. So E1 and E2 are the energy of these two particles coming in. I'm just using energy and momentum conservation to write down the right propagators. Okay. Okay, and then minus I V of K, and then P prime. So out here, P comes in. This is P, and out comes, there's a P prime. Maybe this one's, P prime comes out here. This is minus P prime. Okay, by energy conservation, the square of these two, there's a minus sign. By energy conservation, these two are, the squares are the same, but in the middle, the square is not the same. That's why I went over there and I defined those coefficients in some particular way. And then d cubed q uh, 2 pi cubed d omega over 2 pi. Okay. So that's what I have to do. So first thing is these vertices do not know about the energy omega. They don't know about so the energy integral, this omega integral, it only knows about these propagators. So I just have to do that integral. So let's define I delta is equal to I over E is equal to the integral d omega over 2 pi. Okay, then I have my two propagators, so that would be I over omega minus the square root of k square plus m1 square, and there's a plus I epsilon. You want to be careful with that. There's an I over E1 plus E2 minus omega, the square root minus the square root of k square plus m2 square, okay, plus I epsilon. So you look at that integral. You can actually close this guy up or down, it doesn't matter. If you close up, you pick up one of the residues. If you close down, you pick up the other residue. Either way, you get the same answer. And the answer that you get is that this is equal to I over E, where let me define E just is E1 plus E2. And so if I substitute omega equals the square root of k squared plus m1 squared in here, right, you see I get E1 plus E2, and then I get this and that together. So I have minus the square root of k squared plus m1 squared minus the square root of k squared plus m2 squared. Okay. Now this thing, we need to process somehow to organize it, because one of the issues is that in this effective field theory, notice it's a low energy effect. It's a low energy effective field theory. It's a low energy effective field theory, but there are pieces in here which are quantum, and we want to throw all that stuff away. We're not interested in that. We want to reorganize it a little bit. And the little trick for reorganizing it is the masses, m1 square is equal to E1 square minus P1 square. M2 square is equal to E2 square minus P2 square. So let's do that. So this is then equal to I over E, where E is the sum of the energies, minus the square root of k square minus p square plus E1 square minus the square root of k square minus p square plus E2 square. Okay? And then there's a little observation. This minus that, see if you look at the vertex, so let's say there's P here, I guess it's P and there's K, so this comes in. P minus K see that thing, P minus K square minus P square, well, what is that? Sorry, I wrote this the wrong way. Where's the, sorry. So K is equal to P, and let's say we're looking at like this. Let's draw it like this. So there's Q coming down, and this can this we know how to interpret it. It's very much like the graviton momentum. And remember, this thing is quantum. There's like an H bar associated with this. So when we do our counting, so here's P, here's K. This Q we can rewrite. We can use that K, go like this, is equal to P minus Q. So when we look at K square minus P square, this thing we can write as P minus Q square minus P square. So this thing then behaves like P dot Q to P dot Q with a minus sign, and then plus Q square. So you notice that this thing is quantum. You know, it's got an extra, like a H bar. The Q's count like H bars according to the counting we had. So that tells you what you need to do to this thing is you want to series expand relative to E. So E carries the mass. That's classical. This has pieces in it that are quantum, so we want to series expand this guy. Right? And the series expansion is we want to series expand in this difference because this difference goes like Q. Q, according to the counting that we had, also in the full theory, is quantum suppressed. So that you're doing a series expansion. The basic idea is you're going to take this integral, all of it, and you're going to series expand everything. Okay, I'm not going to do that. So remember, this thing has a super classical piece, like 1 over Q than it should for classical. That's the iteration piece. So you series expand until the classical order, and you keep all the terms that you get. Okay, that's going to actually be a homework assignment, but let me show you a few things about how that works. So the first thing is this thing, the delta. If we series expand, this thing is going to be 1 over E, and then minus, let me pull out over here, let me pull out the E, E1, so minus E1, and then the first term in the series expansion, this is small, this is the large thing we're pulling out, so that's going to be 1 plus 1/2, and then K square minus P square plus dot, dot, dot. And then we're going to series expand this guy. This is small, that's large. And plus, that should be minus E2, and then 1 plus 1/2, and then it'll be K square minus P square. Oh, and this should have been divided by, since I'm pulling out, I need to divide by E1 square here, plus dot, 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 divided by E2 square plus dot, dot, dot. Okay, I series expand this fellow. This first E cancels E, minus E1 minus E2, that's the one that cancels. So what I'm left with is that I delta. Right, so it's those propagators that I'm working out. So what I'm left with is that this is equal to 2I E1 E2, and you clean it up, divided by E1 plus E2. That's E. That's E equals E1 plus E2, and then K square minus P square. Okay, and then plus higher order terms in this expansion. Okay. So the second term, so if we look the second term here, so you see the amplitude. The first term is kind of trivial. If we're looking at the G square, that just has a C2 in it. You just look up there. It's exactly the C2. It's the second term that's more complicated. And what we get, that second term in mg squared, what it becomes is integral 4 pi C1 1/2 P square plus K square P minus K square 2 minus 2 E1 E2 E1 plus E2 k squared minus p squared, and then 4 pi c1 1/2 p prime square plus k square divided by p prime minus k, the absolute value. Let's put an absolute value on this. Okay, so this was from the potential. I'm just reading we look up there, see the V, the first term, that's this thing. Here was the delta, and here's the second potential. And then I have to integrate d cubed k over d cubed k. Actually, I should make this d minus 1. D minus 1. The reason why I need to do that is because, in fact, this thing is going to be singular. And then what we want to do is make a little change of variables to expose the quantum counting. This over here is a graviton. This is graviton momentum, so we should write it in terms of the graviton momentum. So let's make a little change of variables. We're going to take k is equal to p plus l. Okay, and that means that this 1 over p minus k, okay, 1 over p minus k squared, that this goes to 1 over L squared. So that's the graviton. That's the graviton propagator, or the space components of the graviton propagator. And the same thing we can do on the other side. Squared. Okay. And then we can also, under that change of variables, 1 over this propagator here, k squared minus p squared. This thing we can rewrite as 1 over 2p dot L plus L squared. Then we series expand. We're anyway going to series expand this. That you have to do for homework. Expand everything to the appropriate order, every contribution you get. And the reason why I'm making this change of variables is because it'll help us match to the full theory where we used these momenta. See, the momentum L, the graviton momentum, is the variable. Okay. In the EFT, it wasn't natural because the EFT is that graviton has been integrated out. It's just part of the potential. Okay? So you have to actually do some work here, but it's not that hard. You just have to sit down and kind of take these expressions, and you have to series expand them. You make this change of variables. You series expand everything to the appropriate classical order. This has 1 power of 1 over q too many, so you have to series expand at, 1 more term. And let me actually give you the answer. So for homework, series expand. And then do the integrals. There's integrals. If you don't know how to do the integrals, there's a book, Smirnov. You can find it in basically Feynman integrals. He'll tell you the integral. There's some, essentially they're like bubble integrals that you have to do. And if you do that, you'll find that the effective field theory, that the answer looks like this: minus 2 pi square C2. C2 is the coefficient we don't know, right? C2 is the coefficient in the potential, but we haven't figured it out. So this is what we want. This is what we want. okay, divided by q. And then plus pi square d square. So this is coming out of evaluating this diagram. We're evaluating this diagram. From evaluating that diagram, you get E. C, let me define E. I already did that, E1 plus E2. This variable C, let me put it somewhere else. Actually, let me put it over here. So E is E1 plus E2. And then this variable C is going to be E1, E2 divided by E squared. It's just a way of writing it. Okay, so I just introduce that. And then Q. And then 1 minus 3C, C1 squared. And then plus 4C squared, E squared, C1 prime, which I'll define in a second. Put parentheses around here. C1 prime is equal to dC1 dP squared. So whatever the argument is. So let's say that the argument C1 prime of P squared, that's equal to, by definition, d by dP squared of C1 of P squared. Okay, where did this thing come from? Well, I have to series expand. So there's, there's C's, and I have to series expand this, basically one more power in Q. That's where this derivative came from. Okay. Now, these are known functions. C1, this is known. All of this is known. And there's one more term. The extra guy, there's one more term. I can't let that too big, but C1 prime of P square is d by dP square of C1 of P square. Okay, and then plus 32 pi square U square E C C1 square, and then times an integral dd minus 1, which I'm not going to integrate. You could actually work this out. Smirnov will help you. L minus Q squared, and then 2p dot L. Okay, so what is everything here? That's a graviton propagator, but only the space component. Graviton propagator, only the space component. And this thing, it's this guy. It's the matter propagator, but I series expand. This is higher order. Okay. And of course, I have to uniformly series expand everything properly and keep things to the order, the classical order. Okay. And classical order, we're looking for this piece here. Now, the reason why I'm not going to do that integral is because this integral we can match to the full theory. I'll show you how to do that. This should be L. Okay. So this integral, this is our friend, the iteration. Well, one thing is you can see it has C1 square on it. Now you might say, okay, this also has a C1 square. Maybe that's also part of iteration. But the way we're going to understand this is we will take this and match it to the full theory and recognize that this term, this iteration term, exactly you find in the full theory. So you subtract it from both sides. This is our iteration, which we're not so interested in. The only thing we're interested in here is we take this expression, we go up there. There was a previous answer, including also the triangle coefficients, and we demand that these two be equal. By demanding that the two be equal, we learn what this coefficient is. Okay, but the relationship between the coefficient that we're interested in, the potential, and the amplitude is non-trivial because of these terms. Okay? And this non-triviality has to, in fact, do with the fact that this object, that potential, is not gauge invariant. So you know there's going to be a little bit of complexity in it, and that's what you see here in the matching. But this complexity that you see here, these terms, it's not a big deal in the sense it's known. We know what C1 is, right? That's determined by tree level. And this will cancel, and we're going to be left with this thing by moving these terms to the other side in the match. Okay? But let me just give this thing a name. Maybe I'll put this on a blackboard. The iteration term. I should have enough time to get to it. Let's see, the iteration term. So this is like the boring term that we're not interested in, but we just want to get rid of it. So let's define that to be 32 pi square t square e c c1 square, and let's call it I3d. I3d is just this integral. So I just copied, well, if you can read what I wrote here, but I just copied what's written here, and there's an integral here. Okay, and this integral is infrared singular. Okay, and what's the meaning of the infrared singularity? What's the physical meaning? Well, I'd say it's not interesting. It's an iteration term. It's not anything we're really interested in. It is infrared singular, but this integral has an infrared singularity. That's why I use dimensional regularization. That amplitude up there also has an infrared singularity, right? As long as they match and we cancel them, it's irrelevant what it is. That's the logic of how we're approaching this. Okay, so you might say, okay, but why are you doing it this way? Why don't you just do the damn integral? It's a one-loop problem. And indeed, you're right. At one loop, you can do it any way you like. You don't need all this stuff I'm talking about. Oh, there's iteration, and you want to do matching, and I mean, you know, it's shall we say, overkill. But what happens, this procedure that I'm following here, this logic of how I'm doing it with matching, and I want, this EFT to use, we really need this, in a sense, to straighten out exactly how higher loops works. So in a sense, this procedure I'm explaining here, it's not designed for one loop, because that would be, I would say, quite a bit of overkill on a relatively simple problem. But it's a procedure designed so that we can attack the higher loop problem. Okay. Now, let's see what happens let's see if we can identify the iteration, exactly that integral, this unwanted contribution, this iteration contribution. Let's see if we can identify it up there. And remember I said there's something important that happens where the coefficient of the box and the cross box, they have equal coefficient. And in fact, that's going to be the key. So let's look at, so recall in the full theory, we had that the box and cross box, they come in exactly in this combination with a single coefficient, which, well, we can call it CB, a GR, right? In this combination, this is a special combination. In fact, this combination is exactly how we're going to understand the iteration. So let's write this down. Integral d dl over 2 pi to the d. L squared, L minus Q squared. This is now 4-dimensional, really d-dimensional. That was, notice the integral there is d minus 1-dimensional. So if I'm going to match them, I have to do one integral here, the energy integral. I have to get rid of that. L plus P1 square minus M1 square plus I epsilon. Okay, then times, if I'm adding up the two boxes, it's L minus P2 square minus M2 square plus I epsilon plus 1 over L minus P3 square minus M2 square plus I epsilon. Okay, now we're going to do the expansion. L, remember we could take L or Q to be small compared to P. This is quantum, this is classical, so we expand. And let's look at this thing, that factor, whoops. So that factor, if we expand, we're just going to keep the leading one. That's the L dot P2 term. The M's cancel. So this just becomes minus 2P2 dot L. I can maybe the arrow the other way because I'm actually doing an expansion in here. This will be, at the end, there'll be plus order. There'll be higher order in L that I'm, and there'll be some higher order in L that I'm keeping. I guess order L to the 0. And then plus 1 over 2P3 dot L with the minus sign. Okay, let's look at that. So this thing, it's very important. I should keep my I epsilons. The key is the I epsilon. Let me keep my I epsilons here. Plus I epsilon. Plus 1 over the minus 2P3 dot L plus I epsilon. Okay, plus, I'm going to order L to the 0. So we're just looking at the leading term in the expansion. That's the one that'll be the iteration piece. Okay. Now let's look at that, and we notice that P3 is equal to P2, or it's equal to Q minus P2. Right, so I can replace P3 with minus P2. This is higher order in the expansion, so I throw it away or I put it in there. So this thing flips the sign. Let's make this with a plus sign, and I'll make this a P2. Okay. So you notice this thing wants to cancel. Except for the I epsilons, right? And in fact, this thing, right? So it's difference between expressions that want to cancel except the I epsilons get in the way. And I could put the minus sign here, and I'll flip the I epsilon, right? So this is a delta function. Now that delta function is actually profound. So what is this delta function doing? I want my eraser. So this thing now goes to a delta function minus 2 pi I delta of 2p dot L, p2 dot L. What is this? 2p2 dot L, that's the matter propagator here. It's this matter propagator. So this is, okay, this one, p2, 2, 1. This is, this propagator is 1 over 2 p2 dot L right here. Okay, this propagator. This is L. It's putting this thing on shell. Now, that's not a surprise. Remember, these are classical objects. You want them to be on shell, don't you? Right? So it's happening as we go to the classical limit. The combination of propagators, this combination, is such that it's forcing the matter line to go on shell. Now, if the matter line goes on shell, right, we can do the integral pretty easily. The energy integral is very easy to do now. So we can reduce this from a d-dimensional to a d-1 dimensional by using the delta function that comes from the propagators of this twist, right? This propagator plus that propagator gives us the delta function that allows us, first we put the matter on shell. There's a matter line that goes on shell, and then on top of it, we're going to go to a d-1 dimensional integral, and in fact, we're going to go to this integral. That's the basic idea. Now, the fact that the energy integral becomes trivial should not surprise you, because remember in the quantum theory, the reason why there's an independent energy integral from a momentum integral is, Heisenberg uncertainty principle, right? The relationship between energy and momentum doesn't have to hold for the virtual particles. We're dealing with classical physics. The thing has to localize, right? And that localization is exactly because of the right combination of propagators that appear such that we extract a delta function that forces the energy to satisfy a classical on-shell conditions. No Heisenberg uncertainty principle. Okay, now I see I'm running out of time, but there's a delta function, this thing. So this thing you now write out in components because we need to do the energy integral, so you want to separate that out. So this thing, minus I pi over E2 delta of L0 minus plus P dot L. So P2, we have, let's say there's P2 here, but remember in P2 is equal to E2 and minus P. We're in center of mass coordinates, so when you see the P without a label on it, okay, that's the center of mass momentum. So that's shared. This momentum is actually shared by particle 1 and particle 2. Particle 2 has a minus P, particle 1 has a plus P, but one momentum. That's what happened here. And then divided by E2. So now I guess the homework is, well, you gotta now go ahead and just do the energy integral. Right? So this thing turned into a delta function. A delta function, what you do is, in here you apply the delta function in this propagator. In these propagators, remember we're talking about gravitons to extract the potential, right? the potential means that there's no time is taken out of the graviton propagation. It's instantaneous. That's what the potential is. That means these guys, I can do it right now. Let me just, there's minus signs. Okay. Every time I do that, there's 2 minus signs. So maybe it doesn't matter. So this I put immediately, just by knowing I want potential modes, that I want the potential, I put the graviton propagators, I put those into the spatial components, and then I use this delta function here, this delta function. I use that to solve for the L0 that I see in here. Okay, and then let me maybe write down the answer. I see I am running out of some time. And the answer for this integral, let's see where I can put it. Oh, good, I can put it right here. Okay, so this integral, so all of this combination, that integral, when you just do that substitution, you get 1 over E1 plus E2. This combination comes out just from, you solve, see there's the delta function, and you solve for it and you plug back in here. You'll get this combination out when you clean it up. And then integral d minus 1 over 2 pi to the d minus 1, 1 over L square, L minus Q square, and then 2p dot L. And let me just clean up a little more this blackboard. Now, where have I seen that integral? See? It's the same integral. This and this integral are identical, right? That's going to be the match, the iteration. So let's call this thing, this integral, well, there's a coefficient, 1 over E1 plus E2. And then it's let's call it a 3D integral. Okay, it's d minus 1, it's infrared singular, so maybe I need dimensional regularization, but it's a 3-dimensional integral. This is my 3-dimensional integral right here, same integral. So one is in the EFT, one is in the full theory. The two are going to be identical. Okay, so yeah, I'll just need another 5 minutes or so. Okay, so now, okay, I worked out this plus this together forms, you go through it and you do the integral, the energy integral, you get exactly the same integral as you got here, but there's a coefficient. So now we have to go look up there, what's the coefficient? And you have to plug it in. And you can almost see it. Well, I mean, you got to look what's up there. But in fact, it'll be identical. So let me just say, if we include, let me just say it in words. So for homework, you can verify that my words are correct. That if I just take the coefficients we worked out before, I stick it in front of this thing. Another color. After including the coefficient, it matches the EFT. And the EFT knows exactly what the right answer is because we know what C1 is, right? That's from the tree level, right? So this matches that, and we say that the full theory matches the EFT on the iteration part. But what about the rest of it? Well, the rest of it is very simple because whatever the rest of it is, you just demand that C2 works, right? So you equate this now to the full theory answer, observing that on the left and right-hand side, you have exactly the same iteration term. So therefore, we can solve for C2 directly in terms of the answer that's up there. Yeah. And you have to work out you have to know the value of the triangle integral, which I think I gave that last time. The triangle integral, I think it was 32 pi q, if I remember. Maybe I have that number wrong. Well, it's in my notes. If I can find it. Okay, but okay. So let me actually write down. If you assemble everything, so we do the matching and. Okay, so maybe I'll write it over there. So if we match the EFT to the full theory, okay, then what we find, okay, this potential was the sum of some coefficients, Ci, and then G over R to the I, to the ith power. Let's make it the nth power. N equals 1 to infinity. Okay, then the first two coefficients by doing this matching procedure. The first one we did yesterday, and this coefficient from yesterday, m1 square, m2 square, 1 minus 2 sigma square. And remember, Newton is contained in here in the static limit. And then C2 is a more complicated beast. C2 is nu square. Nu is equal to m1, m2 divided by m1 plus m2 squared. It's a variable that people like. It looks like the reduced mass, except the way it's defined, the m1 plus m2 square. M1 plus m2 is squared, so it's not the reduced mass, but it's essentially the reduced mass up to an extra factor of the total mass in the denominator. M cubed, so m is equal to m1 plus m2. Divided by xc, gamma square, so let's define those as well. So xc I defined as E1 plus E2, E1, E2 divided by E1 plus E2 square. Gamma is defined as E1 plus E2 divided by M1 plus M2. Okay, it gets a little bit complicated, all these variables, but it is relatively high order in perturbation theory. Okay, 3/4 1 minus 5 sigma square minus 4 nu sigma, 1 minus 2 sigma square divided by gamma xi plus nu square, 1 minus xi, 1 minus 2 sigma squared, that thing squared, divided by 2 gamma cubed xi squared. Okay, that's the answer. Okay, looks a little bit messy, but this thing contains all orders in velocity, both of these expressions, this coefficient, all orders in velocity. The first term is in the static limit, it's Newton. The second term contains a piece that was worked out by Einstein, Infeld, and Hoffman. They did first post-Newtonian. First post-Newtonian, it contains 1 power of v square extra. There's a g times v square. Like in here, there's velocity dependence in here. Right, so it's like a g times a v square. That's first post-Newtonian. It also contains a g squared term in the static limit. That's also hidden in here. So this is the generalization of what Einstein, Infeld, and Hoffman had done in first post-Newtonian. Okay? Now, this procedure, the same procedure, including, there was actually something I snuck in. It's very important. I said something like, well, these gravitons, we have to take them into the potential region. That's where the conservative potential is to be found. And that idea, those words, become much more important as you go to higher loops. You work your way up in the perturbation theory. At this level, there's many ways to do it, but the higher you go, the more complicated the integrals. So you want to take advantage of what's called the method of regions, where you analyze the integrals in the region you're interested in. Like we want to get rid of the quantum effects, and we also want to keep only the conservative part. And that's part of this little trick I did, where right there, the propagator, the graviton propagator was replaced with just the spatial part. Okay? And this is the procedure this basic procedure has been carried all the way to order g to the 4th. At order g cubed, it's fairly straightforward. The basic ideas are just laid out. They just work straightforwardly. Fun starts at the next order, at the g to the 4th. So g cubed, it's what I told you. It's just a little more complicated. G to the 4th, some real fun starts. Because we're doing something evil here. Right? We're trying to define the dynamics in terms of a potential which is instantaneous in time. Now, you might worry that at some order of perturbation theory, you can't do that. Right? And the reason why people do this generally, I think, is because Newton did it. So work for Newton, so it's work for us, right? But it's some order of perturbation theory that does not work so well. And non-localities enter. And that is known as the tail effect. So at order g to the 4th, something called the tail effect happens. And what the tail effect is that the dynamics no longer is local. It depends on the past history. And it depends on it in some particular way that's relatively simple, but it still depends on the past dynamics. And what that means is that if you write down a Hamiltonian, you go through this procedure, we get a potential Hamiltonian, and that Hamiltonian, we verify by the matching procedure that it gives us the correct scattering. So that means for an unbound orbit, we know exactly what this dynamics is, the Hamiltonian, the scattering angle, we know all the observables. And now, I don't know, maybe you learned this in elementary school, if hyperbolic motion is the same as elliptical motion, right? The solution that you get for a Newtonian motion, whether it's elliptical or hyperbolic, it's all the same. You continue very easily. That no longer holds. And that's this non-local effect. Now, you might say, well, look, this is a problem with the scattering amplitudes. And, I mean, it is a problem that now we have this tail effect that's annoying us and making it very difficult to continue from the hyperbolic motion, the unbound orbit, to the bound orbit. But it's a problem for everyone. No matter how you do it, there's no simple analytic continuation as far as we can tell. And that's one of the problems that we need to solve. We'll figure out how to do this analytic continuation. Now, you say, what's the source of this problem? Let me actually draw something. So let me draw some gravitons. Can you see that? What's the source of that problem? Well, these are potential gravitons discussed in the way that I said, oh, just ignore the time component of the energy. Well, now we can have a contribution that looks like this, where a graviton goes out, and it's now a radiation graviton. It heads out, it bounces off the potential. We call this thing P tilde. I mean, it's basically a potential. It's basically a potential. It bounces off, you could say, the curvature, so to speak. And it comes back. And the problem is that you get a time non-locality, because you get an effect from the past into the future depending on how this graviton went out and came back. And that, in a sense, is the source of this problem. This tail effect, it was known long before we entered the game with scattering amplitudes, and it causes an annoyance. But it's just hard to take the dynamics of scattering unbound and relate it to the bound case. And I hope in the next year or so that problem will be solved. But right now it's a slightly annoying problem. There's also some other issues that maybe I want to discuss before finishing. What's very important in this game to make progress is the integrals. So if you're paying attention to Johannes Henn and maybe Lance was talking about integrals, they're very important. These integrals that we have to do, they're just like Feynman integrals. So you may notice the integrals are simpler. See, I have to find a simpler integral. See, this integral that I had to do here, it's simpler because certain combinations of propagators occur in the classical limit. I get some delta functions that help me. But at the end, I have an integral, right? Maybe it's a lower dimensional integral, but it's still an integral. And it's the same type of integral that you find in Feynman diagrams, right? And those become very hard as you go up in order by order and perturbation theory at the not the g to the fourth level, but at the g to the fifth level, the next order, the integrals are much harder, right? And all that stuff that Johannes was talking about, you got to pay attention to it. It's very important. Okay, and maybe I'll finish by just making a few comments about some of the things you're going to hear at the Amplitudes conference. So there'll be a few talks. There will be talks. Let me just list some topics. There will be talks that'll discuss spin. Now, we in quantum field theory, we know a lot about spin, right? Going back to Dirac, right? The spin of the electron and so forth. So spin is something that we're pretty good at. Remember, black holes are points. A Kerr black hole, what is that? It's a spinning particle, not with spin 1/2 like an electron, but with large spin. But that's something that we understand quite well how to do in quantum field theory. So there's going to be, I think, 2 talks So I'll say something about it. I think Mogul. Mogul, I think, will use world line formalism. Now, there are extra things about spin that, it's not directly what I was talking about. I was talking about spinless, but it's the same principles, right? Instead of having a scalar particle, we put a spinning particle here, and then the logic is exactly the same, exactly how we do it. Everything about the EFT and the matching and how you integrate and the combinations of integrals that appear, all of that is the same. Here's an interesting one, multi-particle interactions. So this will be Jones. Callum Jones will speak about that. So in Newtonian mechanics, right, the way it works is I have a particle here and a particle there, they interact. I put in a third particle, the way it interacts is individually with the other ones, right? Does it work that way in general relativity? Who wants to take a guess? You think it's two-body interactions or not? Well, remember, general relativity is a nonlinear theory, so no way in hell. If you put three particles, there's going to be new interactions that involve all the particles simultaneously, or four particles. They all talk to each other, and everything affects everything else, but not in a two-particle way. Okay, so that's the general relativity idea, nonlinear theory, and so forth. What's the particle physics way? Well, can I draw a Feynman diagram? So let's do a three-particle interaction. So there's a black hole number 1. There's a black hole number 2. And there's a black hole number 3. And they're interacting. Like one is scattering off the other. I can draw a diagram like this, right? That's a three-body interaction. I can draw four-body interactions, and so on and so forth. Each one of these things is different. So I didn't compute that. I'm talking about two-body interactions. So if I'm interested in three black holes interacting, and I want to know what happens, I need to know the three-body potential, which is not a sum over two-body potentials. Anyway, you should listen to this talk. Oh, pardon. Multi. There we go. Multi-particle interactions. Anyway, he'll explain this. I'm sure he'll have this diagram. He'll have other diagrams. Basically, any Feynman diagram that you can draw with that you can't disconnect into like a two-body interaction. In anything that's connected like that, that's a new interaction. That's part of general relativity, and of course we have access to it through particle physics. There's radiation. So I didn't talk about radiation. I was talking about the potential. So radiation. I'm sure David Kossauer will talk about that. And a formalism, which there was no way I could explain it here in the time. It's actually a very nice formalism that they use where they're directly focusing on physical observables, not gauge non-invariant objects like Hamiltonians or potentials, but directly the physical observable. For example, an impulse, a spin kick, like if you have a spin and it interacts and the spin changes, directly observables. And then there'll be the tail effect, our friend the tail effect. So this problematic annoyance that happens at high orders of perturbation theory. So we'll have talks. I think Michelle Levy will speak about that. I'll say something about that. I don't think we're going to give solutions for this problem, but at least we'll talk about the problem. Okay, so I think I'm done. Thanks.
Okay, thank you very much. And thanks, Zvi, for the whole lecture series. Unfortunately, we postponed the questions to the private conversation because we wanted to